Welcome to the MOOCs course Mechanical Unit Operations. The title of this lecture is Motion of Particle through Fluids. Motion of particles through fluids, we have seen most of the multiphase flows wherever mechanical unit operations are involved, or even some unit processes are involved. Then we have seen that there is a kind of relative motion between solid and fluids, and then that relative motion is very much important in designing this contacting equipment wherever these unit operations are taking place, or unit processes are taking place, right. So, that relative velocity can also be represented in terms of some kind of force balance. One can do the force balance and then report it as in terms of a drag coefficient or drag force, right. So, that is what we have seen. So, we have seen in the previous lecture that different types of applications, and then how much important this relative motion between fluids and solids, especially the multiphase flows associated with the mechanical unit operations. We have already seen many mechanical separation processes involve the movement of solid particles or liquid drop through a fluid. So, there may be a relative motion between a fluid drop or a solid particle or kind of thing in a kind of another fluid. So, that is also possible, not necessarily only solid particles, sometimes liquid drops are also translating in a given fluid. Okay. So, that those applications we have seen, but however, we see a few more applications now. Some examples like elimination of dust and fumes from air or flue gas, then removal of solids from liquid waste, recovery of acid mist from the waste gas of an acid plant. So, from the acid plant, whatever the acid mists are there may be, if you releasing them in the air as it is, so that is going to be very dangerous to the environment. So, then what you have to do, you have to separate them and then clean that air, and then only that effluents you can release into the atmosphere. So, these are a few applications. We have already seen several applications. Now, what we see, mechanics of particle motion, right. So, movement of particle through a stationary or a moving fluid requires an external force acting on the particle in general. So, you need to apply some kind of external force that may be based on the gravity. External force may be gravity force, or it can be a kind of centrifugal force, or it can be a kind of electric field, or it can be due to the magnetic field, or it can be because of some kind of pressure difference, etc. So, but there should be some kind of external force, so that a particle can move through a stationary or a moving fluid. This force may come from density difference between the particle and the fluid, as I mentioned, or it may be the result of electric or magnetic fields. So, whatever the force is that arise due to the density difference in general, or maybe we can say that a gravitational force or centrifugal forces. So, in this particular lecture, we are considering only two types of external forces while developing this motion of particle through fluids. So, those two types of forces are the gravitational and centrifugal forces. Now, forces acting on a particle moving through a fluid, that is what we are going to see. So, what we are considering here, we are considering only external force due to the gravitational forces or centrifugal forces. Those two kind of external forces we are considering. But when a particle moving through a fluid, then it may also be experiencing other forces like buoyant force, which acts parallel with external force, but in opposite direction. Then drag force, which appears whenever there is a relative motion between the particles and fluid, and then this drag force acts to oppose the motion and acts parallel with the direction of movement, but in the opposite direction in general, if kind of a one dimensional flow. But in general, direction of movement of the particle relative to the fluid may not be parallel with the direction of external and buoyant forces, and then the drag force under such conditions makes an angle with the other two. So, because of that one, we need to find out the individual component of the drag force rather than having a kind of total drag force directly. So, this kind of cases where drag force making an angle with the other two kind of forces is called as a kind of two dimensional force in general, and then drag must be resolved into the components. Okay. Like individual pressure drag component you have to find out, individual friction drag component you have to find, something like that. In the previous lecture, when we were defining the drag forces or developing relation for the drag forces, we have taken a surface like this, right. So, this surface like this, and then we have taken a kind of element on this surface, right. So, and then fluid motion is coming in this direction u naught. So, now the drag force is the force acting on the solid object exerted by the fluid in the direction of the flow direction, in the direction of the flow. So, but now the flow direction in horizontal, and then this surface is making an angle with this surface. So, if you take this angle like this, so this angle something like making some angle. So, that angle, based on that angle we have derived the components. So, since it is making some kind of angle with this surface, what we have, we will have in general different components. You have to find out a kind of pressure component normal to the surface, and then you have to find out a tangential component like this. So, whatever the pressure force, and then tau w dA, let us say if this is the dA is the area of the element that we have taken, then pressure force would be pdA, and then shear force would be tau w dA, and they are in two different directions. So, this is the flow direction, but the PDA is acting in this direction, and then tau WDA is acting in this direction. Force due to the pressure and force due to the shearing action are acting in two different directions compared to the this direction. So, that is the reason these kind of flows we call it a kind of two-dimensional flows, and then we have to obtain their kind of the components, we have to obtain the components of these forces acting in the flow direction. So, now in the horizontal direction we have seen that this is kind of a this force is there. So, then based on the angle we have seen. So, here also we have seen based on the angle how much is this things that force it acting in this direction. So, that also we have seen. So, we have seen this tau w, and then this angle is a kind of 90 minus alpha. So, this component would be tau w sin 90 minus alpha dA. So, that is tau w cos alpha dA is in the other direction, in this direction that is acting, whereas in this direction whatever that acting is tau w cos 90 minus alpha dA. So, this is tau w sin alpha dA. So, the wall drag that is acting in the flow direction for this element is tau w sin alpha. Similarly, here if it is 90 minus alpha degrees, so then it will be alpha. So, then this would be, this component would be p dA sin alpha, and then this component in the flow direction would be p dA cos alpha. So, this p cos alpha dA is going to be the form drag that is acting in the flow direction, though the element is not having a kind of one dimensional flow. That is the flow direction, and then the alignment, the angle that is making with the flow direction, this element they are not same, but then it is a two-dimensional flow. That is the reason it is a two-dimensional flow. Under such conditions we have to find out a kind of individual components of the drag force, and then add them together to get a kind of a total drag force, right. But in this lecture what we will do, we will be considering only one dimensional motion of particle through fluid, okay. So, that to avoid complications, and then have a kind of simplified analysis, because whenever there is a two dimensional flow, it becomes very difficult to get the results analytically, and then one may need to go for semi analytic or semi numerical or numerical results, or by experimental approach only. So, one dimensional motion of a particle through fluid, if we consider that, we can do analytical analysis, simplification, and then obtain the drag forces, total drag force, how much it is, how much total drag force acting on a particle when it is settling in a kind of gravity motion or centrifugal motion. That is what we are going to see, provided the motion is one dimensional motion. Let us consider a container, very large container, right, in which we are settling a particle of small particle size, right. So, large container we have taken in order to have a kind of unbounded motion of particle in infinitely long cylindrical column. This we are trying to do because in order to have a kind of free settling conditions, So, this is very much important because the analysis that we are going to do, that is only for free settling condition. How to make sure that the the particle settling conditions are under free settling condition, you can make sure by having a unbounded flow and then no other particles nearby there are no other particles, and then container wall is also far away from the particle. By taking these things, you can make sure that a kind of the particle is settling under free settling conditions without any kind of hindrance from the neighboring particles or without any kind of hindrance from the container wall. So, now this particle, it is settling. It is when it is settling, initially the acceleration of the particle, acceleration of the particle may be there, so that it may be settling with certain velocity, but du by dt, let us say u is the velocity of particle that is settling, right. When it is settling, initial conditions du by dt is not 0 actually, but if you provide free settling conditions without any hindrance and then without any neighboring hindrance because of the neighboring particles or wall containers. So, eventually what will happen at certain location when it reaches a kind of free settling conditions achieved. So, from here onwards what you have du by dt is equals to 0. So, under the free settling conditions, and then what we can expect, that you can expect that du by dt is going to be 0, and that is going to be there again not up to the entire bottom when it reaches the bottom of the container, but to some extent, it du by dt remains 0. So, this is the du by dt is 0, that means u is maximum here. So, maximum attainable velocity. So, under the free settling conditions, what we can have, the particle maximum attainable velocity whatever is there. So, that velocity we call it as ut or terminal velocity or free settling velocity, that is what we called it, right. So, this terminal velocity we are going to use this analysis. So, this terminal velocity ut is related to the drag coefficient. That is what we are going to see now. How it is related and all those things, that is we are going to develop now relations. Okay. So, this is the basically the assumptions or the simplification of the flow condition that we are taking. So, what we are taking? We are taking a infinitely long cylinder filled with a kind of liquid, some kind of liquid in which you are trying to settle this particle, or you are trying to find out the velocity of the particle, or you are trying to find out the drag experienced by this particle when it is settling in a column of liquid. So, you are taking infinitely long column, large diameter and then large length, large height cylindrical column you have taken, and then you filled a kind of liquid. In this liquid you are allowing one small particle to settle down, right, when it is settling. So, under the initial condition, settling conditions, du by dt may not be indeed that will not be equal to 0, that is from one location to the other location when the particles falls, the velocity will not be remain same. Let us say from this is the at t is equals to 0, at t is equals to t1, it may be coming here. So, whatever the u1 is there, that is not same. By this time it t2 u2, that is not same as the u1. So, at T3, let us say particle reached to this point. So, that means at T3 the whatever the velocity, let us say u3, that is not same with u2. So, that means from distance and from time, the particle, the velocity, the settling velocity is different in this region, and this is known as the non-free settling region. But after certain distance, what happened, particle attains a kind of free settling conditions where the particle, the velocity is found to be independent of the time and then independent of the distance, whether you measure at this location, at this location, at this location, or at this location. As long as the free settling or terminal velocity conditions are prevailing, it will be having the same velocity. So, that is the reason du by dt is equals to 0. So, that means when this du by dt becoming 0, that condition, maximum velocity condition prevails, that maximum velocity is known as the terminal velocity, right. So, this is what we are going to develop the relations for the between this ut, cd, and then other kind of things, other kind of forces that are acting, that I mean, like we are going to make a force balance and then trying to develop these relations, suitable relations. Okay. So, now the same thing you consider here. So, whatever we have discussed till now, there is a particle, but I have drawn in a kind of smaller geometry, so that to include the other terms also. So, now we have a container, we have a particle, and then that is settling with the gravity. So, the gravitational force Fg is acting downwards here. So, there will be a kind of buoyant force that will be acting opposite to the whatever the force is causing the motion. So, buoyancy is acting opposite to Fg here. So, that is buoyant force Fb is acting opposite to Fg. Now, this particle, when it is settling here, right, so the fluid is offering some kind of resistance, it is not allowing to, it will try to resist the particle motion. So, that resistance is known as the drag force. So, that drag force will also act opposite to the direction of the movement. So, that is Fd is acting in the opposite direction to Fg as well here, right. So, the same thing if you take a generalized one. So, like not necessarily that flow is a kind of vertical ones. If you have a kind of flow like this, and then there is a kind of some external force Fe which is causing this particle motion in a kind of horizontal direction as shown here. So, then it is exactly the similar way, balance has to be done exactly the similar way. Okay. Only thing that Fg is replaced by Fe. So, what we do, we start with the generalized one with Fe, then for Fe we substitute Fg if you wanted to know the motion because of the gravitational force, and then for Fe we substitute Fc, that centrifugal force, if you wanted to know the motion of the particle because of the centrifugal force. So, let us assume mass of the particle m is constant, whose density is rho p. The projected area of the particle is AP. Okay. So, for simplification I have shown a kind of spherical particles, a kind of circle, but whichever particle you take, the projected area of that particle you have to take, that is, let us take let us say AP. We first generalized one and then we apply the case for the kind of spherical particles. Okay. Now, consider a particle of mass m moving through a fluid under the external force Fe. Now, let the velocity of particle relative to the fluid be u, then the buoyant force on the particle is Fb as I mentioned, drag force offered is Fd, then acceleration of particle is du by dt. Now, what we try to do? We try to find out what is this Fb, what is this Fd, and then what is this Fe, right. Then we make this balance, like Fe minus Fb minus Fd is equals to the net force, that is m du by dt. Then we simplify this equation in order to get the free settling velocity ut, right. Remember, all these things are for the free settling velocity condition as I explained just before. So, force balance, net force F is equals to m du by dt or d by dt of mu. So, in our case the mass of the particle is constant. So, that means m du by dt is equals to Fe minus Fb minus Fd. This is the overall force that is acting on the particle, that is external force causing the motion minus the buoyant force that is working opposite direction to the external force, and then drag force which is offering resistance to the motion. So, Fb minus Fb, Fe minus Fb minus Fd, that is the net force that is acting on the particle at a given instant, and then that should be equal to the m du by dt, right. So, now we have to find out what is this Fe, what is this Fb, what is this Fd, that is external buoyant and drag forces. Individually we have to find out, we have to substitute here in order to get an expression for this u in terms of known parameters like rho, mu, rho p, and then dp, particle diameter, etc., that we have to do. First we do for a kind of generalized case, then we take a spherical particle case. So, external force, if the acceleration due to the external force is Ae, then m into Ae should be external force, that is quite clear. And then drag force, we have already seen the definition, CD is equals to Fd by Ap divided by half rho u square. This is what the definition of the drag coefficient that we have seen in the previous lecture. So, from here Fd we can write in terms of CD as CD rho u square Ap divided by 2. So, out of these three forces, external force and then drag force, we have an expression already, right. Now, we have to find out the expression for the buoyant force, right. So, buoyant force is the mass of fluid displaced multiplied by the acceleration from the external force. So, let us say this particle we are having here. So, how to, this is only thing that here you have to find out mass of the fluid that is displaced. So, let us say this is the particle here, okay, that we have taken. Now, when it is coming here, just underneath it like this. So, that means whatever the fluid that was here, initially particle was here, right. When it is just falling down, let us say it has come here. So, whatever the fluid that was present here, this shaded portion, that fluid is being replaced by particle. So, whatever the volume was there here, that volume is replaced by the particle. So, and that volume is same as the particle volume. So, that is m by rho p. So, this is the volume of the fluid displaced by the particle. This is the volume of the fluid, m by rho p is the volume of the fluid displaced by the particle, right. Because it is same, whatever the volume of the particle is there, that much volume only, that is going to, that much volume of the fluid only that particle is going to replace. So, m by rho p, whatever the volume of the particle is there, same volume of that much volume of the fluid is being replaced by the particle. But we need to know mass of the fluid displaced. So, now this is the volume of the fluid displaced by the particle. If this volume of the fluid, if you multiplied by the density of the fluid, then you will get the mass of the fluid that is being displaced by the particle. So, m by rho p multiplied by rho, this quantity if you multiplied by the Ae, acceleration from external force, then we have this buoyant force. This is according to the Archimedes principle. That is, buoyant force is the product of the mass of the fluid displaced by the particle and the acceleration from the external force. So, volume of particle m by rho p is the volume of fluid is being displaced by the particle. So, mass of the fluid displaced would be m by rho p multiplied by rho. Now, buoyant force should be m rho by rho p multiplied by Ae, that is acceleration from the external force, right. So, now we have this buoyant force also. So, now if we substitute these things in the force balance equation, we will get the final expression for the velocity. So, here this rho is nothing but the fluid density, rho p is nothing but the particle density. So, when you substitute, m du by dt is same in the left hand side, the force balance equation. This is the external force, this is the buoyant force, and this is the drag force, right. So, that means m if you take to the right hand side, and then from these two terms if you take m common, so then you have Ae multiplied by rho p minus rho by rho p. We are doing, you will get something like Ae into 1 minus rho by rho p. If you do LCM, so then you will get this one. So whatever this m is there here, so that m will be cancelled, and then there will be m will be coming out here. Okay. So this second term is remaining same, only this m is coming in the denominator here. Now motion from gravitational force, this is a kind of generalized kind of expression. Now till now here we have not done any kind of this thing, we have not done any kind of specified derivation with respect to the external field. Generalized external field we have taken. Now let us take external field is gravity, that is the particle is settling due to the gravity. So in place of AE you should substitute G, acceleration due to gravity. Then you will get du by dt is equals to G into rho p minus rho by rho p minus CD u square rho AP by 2m. Now terminal velocity, as I already mentioned, is the maximum velocity attained by particle under free settling conditions. So that is du by dt is equals to 0, as I already explained. So we are trying to find out this terminal velocity ut, right? This is ut, u suffix t, t stands for terminal velocity, right? So in this equation, if you make this du by dt is equals to 0 under terminal free settling conditions, then we have ut is equals to whatever this equation, from this equation what we have, G rho p minus rho by rho p is equals to CD u square rho AP by 2m. So u square is equals to G rho p minus rho 2 and then m divided by rho p CD rho AP, and then if you take square root each side, then you have ut is equals to, now this is under terminal condition, so this u should be replaced by the ut, right. So this is true under the condition du by dt is equals to 0, or when du by dt is equals to 0, then u is nothing but ut, terminal velocity. So ut is equals to square root of 2g rho p minus rho m divided by ap rho p CD rho. So now this is the generalized terminal velocity condition for any particle which is settling under one dimensional conditions, one dimensional movement. The motion of the particle is one dimensional in a kind of container, and then the settling is due to the gravity. So this is the velocity expression, generalized expression. It is not specific to any particle, right. So but only assumptions that it is under free settling conditions, that is terminal velocity, that is we are having here. Then now we take to the spherical particle case, right. So how we do that one? Only this previous expression, wherever that ut is equals to square root of 2g rho p minus rho m divided by CD rho p AP rho, that expression, in place of AP we will be writing projected area of spherical particle, that is pi dp square by 4, and then in place of m we will be writing pi dp cube by 6 multiplied by rho, so that mass of the particle, rho p, that is mass of the particle. So let us say if you take the diameter of the spherical particle is dp, then this is the volume, pi dp cube by 6 is the volume of that particle. If you multiply it by rho p, then you will get the mass of the particle. Projected area for a spherical particle is pi dp square by 4. Then in this equation ut is equals to square root of 2g rho p minus rho m divided by ap rho p CD rho. When you substitute, then you will get this expression. So here what we are doing, we are in this equation we are substituting square root of 2g rho p minus rho m is pi dp cube rho p divided by 6, and then this ap is pi dp cube by a is pi dp square by 4, then rho p is as it is CD is as it is, 6 is already there, and then rho is as it is. So this rho p can be cancelled out, this pi can be cancelled out, this pi dp square, and then this cube of dp cube can be cancelled out. So this, if you can 2 ja 2 3 ja, so 4 by 3 you will get. So that is, you will get square root of 4 by 3, g is as it is, rho p minus rho is as it is, and there is a dp as it is, by 3 is there, cd is there, rho is there. So now this is the, when you substitute this one, you will get this equation. So this is what you will get, this equation. Right? In this ut equation, you simply substitute a and m, then you will simplify, then you will get this part, this expression. Now this is the expression for the terminal velocity of this particle, irrespective of which flow it is, whether Stokes regime or whether it is slowly settling or very fastly settling. Only the condition that it should be free settling condition and the terminal velocity condition. So then this is valid. This is valid irrespective of the flow regime, whether the particle is small particle, large particle, slowly settling or very fastly settling. It is not dependent on that one. It is a generalized one, right? Now we have already seen there is a Stokes regime, then Newton's regime of the flow in the previous lecture. If the Reynolds number is very small, then we call it a kind of Stokes regime. REP less than 1, then we called it a Stokes flow regime, and then for that condition CD is equals to 24 by REP. When you substitute that CD is equals to 24 by REP here, then we get a kind of a expression for a Stokes terminal velocity, or the terminal velocity for a spherical particle under Stokes regime. Then similarly for spherical particles, we have that Newton's flow regime, that is, if REP greater than 1000, then CD is equals to 0.4 to 0.45, it varies. Let us take 0.44, that CD value substitute here, then you will get settling velocity of a spherical particle under Newton's flow regime. Whereas this velocity is, it is valid for the entire range of Reynolds number, from very small Reynolds number less than 1 to Reynolds number RE 1000 or even more also, right? Only thing that corresponding CD value one has to substitute here to get the expression. So now, but if you know the CD value, then it is fine, but if you do not know CD value, CD is again function of u or ut here. So that is the reason we need to further do analysis, right? You can use this equation only when you know CD. In order to get this velocity, you should know CD, but again in order to know the CD, you need to know back this ut. So they are interconnected. Without one information, you cannot get this value. So at least one of them should be known. If you know the u, then CD you can calculate. If you know CD, then you can calculate u. So that is what we are going to see. We do step by step. Let us take first case, when the Reynolds number is very small, REP is very smaller than 1, then CD is equals to 24 by REP, that is we have already seen. So that is 24 mu by dp u rho, right? So now here this one we are going to substitute here. So this is under the terminal condition, so this u should be ut. So now in this equation, what we have done here, in place of CD we have written 24, we have to write 24 mu divided by dp ut rho, this we have to substitute here. When you substitute here 24 mu divided by dp ut rho, so we have taken up numerator. So now you further simplify it. Simply what will get, you will get a kind of velocity for a terminal velocity under Stokes flow regime, right? So here this rho is cancelled out, right? And then dp and dp square is there. So ut is already as it is, g rho p minus rho is as it is. This 4 by 3 multiplied 24, that you can write it as a 18, because 4 1 ja 4 6 ja 3 into 6 18. So 18 mu as it is. Now here again inside the square root of right side there is a ut, and then left side is also 1 ut. So, what you do, you take square either side. So, then left hand side you have ut square is equals to g rho p minus rho dp square ut by 18 mu. So, this 1 ut and in the right hand side and square of the ut in the other side would be cancelled out. So, then you will have ut is equals to g dp square rho p minus rho divided by 18 mu. So, this is the velocity, this is the terminal velocity under Stokes flow condition for spherical particles, right. Terminal velocity of a sphere in Stokes flow regime, that is very small Reynolds number. So, similarly now what we are going to do, we are going to do for the Newton's flow regime. For the Newton's flow regime, REP order of 10 power 3 to 2 into 10 power 5, CD is constant. So, that constant let us say 0.44. It varies between 0.44 and 0.45 slightly, but let us take 0.44. So, now in this equation whatever the FD equation is there, so that equation if you substitute this what we have, CD is equals to FD by AP divided by half rho u square, this is what we have. So, from here FD is equals to 1 by 2 CD rho u square AP, right, of 0.44 you can take CD rho ut square and then AP you can take it as pi d square by 4. So, and then this simplify it, you simplify it, then you will get 0.055 pi dp square ut square rho. This is what you get drag force. But drag force is not our interest as of now. Our interest is to find out the motion of the particle, velocity of the particle. So, terminal velocity of the particle. So, in this equation, this is generalized equation that we just derived. Here in this equation, in place of CD, if you substitute 0.44, you will get if you substitute here 0.44, then you have 4 by 3 multiplied by 0.44 under the square root of that, all comes out to be 1.75. So, ut is equals to 1.75 square root of g dp multiplied by rho p minus rho by rho. This is the terminal velocity of a sphere settling in Newton's flow regime, right. So, now we have developed for spherical particle, in general also we have developed the settling velocity of the particle ut etc. We have also developed the settling velocity for a spherical particle, specific to the spherical particle settling in a gravity force. Due to the gravity the particle is settling. So, then depending on the flow regime, we have find out the terminal velocity expressions ut for Stokes flow regime as well as the Newton's flow regime. Indeed, we have also first we have developed a generalized terminal velocity expression, then we applied for a individual Stokes and then Newton's flow regime, right. But those expression, that is terminal velocity of a sphere under Stokes or Newton's flow regime, you can know only if you know the Reynolds number, right. If the Reynolds number is less than 1, then only you can say that it is in Stokes flow regime, and then you can apply that equation. If your Reynolds number is more than 10 power 3, then only you can know that it is a kind of a Newton's flow regime, then only corresponding terminal velocity equation you can use that we have just arrived. But if you want to know the Reynolds number, you need to know the terminal velocity, then only you can use this expression, that is they are interconnected. You need to know the Reynolds number in order to use this equation, right. But in order to find out the Reynolds number, you need the velocity condition. So, there is a connection, they are interconnected. So, you cannot calculate, right. So, that is the reason we are going to develop a criteria which is independent of a velocity term, right. So, or independent of the Reynolds number term. So, that it is just a kind of mathematical simplification, so that we can use them in our this kind of problems kind of thing. Okay. Even without the knowledge of velocity or without the knowledge of Reynolds number, we can find out the terminal velocity accordingly, right. So, that is what we are going to do. We are trying to develop a criteria for settling regime of spherical particles without requiring the knowledge of terminal velocity or the Reynolds number, okay, or the drag coefficient even. Okay, how to do that one? Let us say for Stokes law, we have Rep is equals to dP ut rho by mu, right. So, this is the Reynolds number definition. Rep is equals to dP ut rho by mu. This criteria we are going to develop for two regimes, Stokes regime and Newton's regime, and then we find out a value. So, if that value, that criteria, if it is matching the Stokes regime, then corresponding Stokes regime equations will be using. So, for that this mathematical simplification we are going to do now. This Rep, we know that dP ut rho by mu. Here this ut under the Stokes regime, we have already seen that G dP square rho p minus rho by 18 mu is nothing but ut under the Stokes regime. So, that we are substituting here simply G dP square, 1 dP is already there. So, dP cube, rho is as it is, rho p minus rho is here, and then 18 mu, and then 1 mu is there, 18 mu square, right. So, now it is not having any ut value. Okay. So, now this one what you do, 18 you take to the left hand side from this equation, and then rearrange this equation such that dP multiplied by G rho p minus rho by mu square power 1 by 3. So, whatever the power 1 by 3 to this parenthesis, and then this entire whole power cube, so that it is same as this part, so that it is same as this part, right. So, now here this part, whatever the within the square brackets part is there, so that you write it as k. So, that if you write it as k, k is like dP G rho p minus rho divided by mu square whole power 1 by 3. This is going to be the k factor, right. So, this we are taking as a kind of criteria. Now, here for the Stokes regime, what we have, the maximum value for Rep we can assign as 1 under the Stokes regime, because Rep less than 1 we call it as a kind of a Stokes regime. So, upper limit for the Stokes regime let us take as 1. So, if Rep 1, then Stokes law is applicable, right. So, if Rep is equals to 1, then Stokes law is applicable. So, now in this equation you substitute Rep is equals to 1. So, k is equals to 18 power 1 by 3, that is k is equals to 2.6. So, if Rep is maximum limit of Rep for Stokes flow regime is 1, then corresponding k value is 2.6. Maximum limit of k value for Stokes regime, from here what we understand, it is 2.6. That means, if k less than 2.6, then Stokes regime is applicable. That is, if k less than 2.6, then Stokes law is applicable. And you need to know velocity in order to calculate the Rep, but in order to calculate this k, you do not need velocity. So, that is this quantity. This quantity, that is dP multiplied by G rho delta rho divided by mu square whole power 1 by 3, this quantity you need to find out. It is only function of geometry, size of the particle and then the fluid properties like rho, the density viscosity of the fluid, and then density of the particle. Only that much you need to know. You need to know size and density of the particle, and density and then viscosity of the particle you need to know. Once you know, then you can find out this K value. If this K value is less than 2.6, then you can say that Stokes law is applicable, and then you can use this equation to find out ut, right. So, what we have done, we have in general tried to escape requirement of terminal velocity, because you can calculate use this terminal velocity equation only when you know Reynolds number, and then in order to know the Reynolds number, you need to know this ut. So, they are interconnected. So, that is what we tried to do. We tried to escape of requirement of this ut in order to do these calculations. Now, same thing for the Newton's flow rhythm, REP is 10 power 3 to 2 into 10 power 5. So, we know that REP is dP ut rho by mu. So, dP rho by mu is as it is. Ut under the Newton's flow rhythm is this one we just derived, right. So, this is the ut for Newton's flow rhythm, the previous ut for the Stokes flow rhythm. Okay. So, now here this equation again if you rearrange, what you get? You will get 1.75 multiplied by dP g rho, rho p minus rho by mu square whole power 1 by 3 whole power 1.5. So, this is nothing but again your K value. So, that is 1.75 K power 1.5, right. So, now the lower limit for the Newton's flow rhythm is 1000, 10 power 3. So, lower limit of K would be 68.9. So, that is here in this equation REP is equals to 1.75 K power 1.5. Here you substitute REP is equals to 1000 and then you calculate K. So, it comes out to be 68.9. Upper limit of REP for Newton's flow rhythm is 2 into 10 power 5. So, now this you substitute 2 into 10 power 5 into here in this equation, REP is equals to 1.75 K power 1.5, then you get K value 2360. That means, if your K value is in between 68.9 to 2360, then Newton's flow rhythm is applicable, and then you can use this particular equation for your terminal velocity. Ut is equals to 1.75 square root of g dP rho p minus rho by rho, that you can use. So, K less than 2.6 Stokes regime, K greater than 68.9 is a kind of Newton's regime up to 2360. So, it is a Newton's flow regime. So, whatever between 2.6 to 68.9, it is a intermediate range where we do not have a kind of generalized expression for the velocity. It has to be obtained, calculated using the CD value. So, what we have seen today, now till now we have derived a kind of motion of particle, especially one dimensional motion of particle in an unbounded flow conditions, particle settling under free settling condition, that is without any hindrance due to the neighboring particle or without any kind of hindrance because of the container wall. Under those conditions, if a particle is settling due to the gravity, what is the expression for the terminal velocity? For a generalized case, generalized particle we have derived. Then we have also simplified that expression for a kind of spherical particle settling in a gravity force or gravity field. Then we have developed the velocity expression for the Stokes flow regime and then Newton's flow regime for a spherical particle settling in a gravity field. Then we have also developed the criteria, because the Stokes and Newton's flow regime terminal velocity equations we can use only if we know the Reynolds number, and then Reynolds number is again dependent on this terminal velocity ut. So, they are interconnected. So, in order to avoid the complications, the interconnection of this REP with the ut, what we have tried to do, we tried to develop a criteria in terms of K, and then that K if less than 2.6, we found it is a kind of Stokes flow regime for a spherical particle. If it is between 68.9 to 2360, then it's a kind of Newton's flow regime for a spherical particle settling in a gravity field, and then this k is in between 2.6 to 68.9, then that is a intermediate range. For that range we do not have a kind of generalized UT expressions, so that we have to calculate using the generalized UT expressions. Before developing the Stokes and Newton's flow regime, whatever the UT expression that we have used, which is function of CD, that we have to use, right. In the next lecture, what we will be doing, we will be discussing 3 to 4 problems, example problems on these free settling conditions etc. under the gravity, and then we try to find out how to use this equation. If you know the Reynolds number, it is straightforward. If you do not know Reynolds number, how to calculate this terminal velocity, those kind of things we are going to see in the next lecture. The references for this lecture are given here. The most of the lecture is prepared from this Unit Operations of Chemical Engineering by McCabe, Smith and Harriet book. Then other references, we have Unit Operations of Particulate Solids Theory and Practice by Ortega Revas. Some details of this lecture can also be found in this Carlson and Richardson's Chemical Engineering Series 2nd volume by Richardson and Harker. Transport Processes and Unit Operations. This book by Gion Coplis is also involving some information about the settling of particles in a fluid. Then Unit Operations by Braun et al. And then Introduction to Chemical Engineering by Badger and Banchero. These books are also a kind of good reference books for the today's lecture. Thank you.